Make Alive, as was mentioned in the introduction, it's actually the title of our book. We have one book that is coming out under two titles. First title was Make Alive, and then our publisher took it to the book fair, and it was picked up by Thames and Hudson, and they were like, Make Alive, that's not a good title. Who knows, what buyers of the book won't know what your book is about. We have to call it the living, thinking, breathing buildings of the future. And that was quite a shock to us, but you know, I kind of liked it in a way. That's clear. So let's do that. So we have now 2 books out, identical content, 2 different titles. When you're in academia, that looks very good on your CV. So I'm afraid I'm not solving the world's problems. I'm not, you know, doing, maybe we get to do it accidentally, but so far it hasn't happened yet. But this is a story about architecture in the RAD Lab. We just opened this lab. We think it's a fascinating place, and it does interesting things. I'll get to it. This week I was preparing this talk, which was always a monumentally hard thing to do, and I was obviously procrastinating. And so instead I opened the mail, and I got the Wired of this month, and I looked at the cover, and I was like, hey, that's the introduction to the talk. All right? So let's just take a picture of it, and I'll just read it out loud. So there it is. The Wired of this month. It says, awake. When the objects around us can talk to one another, the elements of our physical universe will converge and spring to life. In time, this network will grow to fulfill our needs, understand our desires, and enable our dreams. And then it says, welcome to the programmable world. Now, even though that's the introduction to the talk, we're not fulfilling anybody's needs yet, or understand anybody's desires, or enable anybody's dreams. I don't think technology can, but maybe we can contribute to it a little bit. And that's the book that we just published, and it's called Make Alive. So awake, make alive. You know, maybe there's a connection there. So, but we have come to these this phenomenon before in various wordings, let's say, right? I mean, lately what I call it is the Internet of Things, but we can sort of slowly go back in time to the 80s, where there was this notion of ubiquitous computing that was launched by the sort of godfather of ubiquitous computing, and that is Mark Weiser. He said ubiquitous computing is roughly the opposite of virtual reality, where virtual reality puts people inside a computer-generated world. Ubiquitous computing focuses the computer to live out here in the world with people. So, as architects and designers, we started to scratch our head. And it's just like, oh, well, if this is the case, right, if computation in the desktop computer is disappearing off the desktop, and it's surrounding the space that we live in, and it's embedded itself in all the objects around us, that's kind of the architect's job, isn't it? Right? But we know nothing about computation. We know nothing about computers. We just merely use them to make pretty drawings that people build. But this is the kind of thing that we have to start thinking about, because supposedly it's our territory. So that's what we did with the lab. So we instantly start applying for grants, joined the university, got us a lab. We are very lucky to find this lab in the Bay subway station. It's literally in the Bay subway station. When you're exiting the Bay subway station, there are 3 exits. One goes to one goes to Cumberland, the other goes to Bay. You go through the center, you basically go through our lab. And it's interesting because that's the way we want it. We want this lab to be a platform where anybody from any discipline can come together, because we think that this issue it requires knowledge of people from many different fields. We can't solve this thing. No, we need many other people. We need plumbers, we need electricians, we need doctors, we need engineers. We need everybody to basically address this issue, because it's not really within one realm. So even though we haven't really lived up to the moment yet where we're in the middle of the city, but maybe that's a good goal. So so it's located there, right? It's actually not in the middle of the campus, but it's on the perimeter of the campus. So it's another kind of lucky accident that we're not in the campus, but sort of on the perimeter, because we like the notion of standing with 1 foot in the academy and 1 foot outside the academy. So we don't only welcome the academics, but we also welcome the amateurs. Fundamentally, this is what the question then became for us as architects. On the left, there is a concrete block. On the right, there's a little computational device. And these things are these days very cheap and available. You can buy these things for, this particular one is an Arduino board. You can buy these things for $9, $10 on the internet, and it's a little computer on a chip. Right? You can program these things, you can put a bunch of sensors in these things, and you can tell this thing, like, if you sense this, do that. So the question for us became, what if the building blocks, and this is not literally a concrete block, even though it looks like one, we see it as a kind of more conceptual question. What if the building blocks that create the space around us become computational? What will it start to do? What will it start to sense, and how will it engage with us? The other question that often comes up is, and it's probably related to the previous question, is that what if every building block around us gets an IP address, right? What if it gets connected to the internet? And if we quickly look at the Internet of Things, and if we quickly look at the new internet protocol that we seem to be using, we used to use IPv4, supposedly. Now we're using IPv6, supposedly. And this is the amount of internet addresses that the IPv6 system has. Now, I have not been with the university long enough to tell you what that number is, but it's 340 undecillion. It's fairly meaningless to me. So we look a little bit further, and for every square meter of the Earth's surface, something like that, right, it is this number, which also remains fairly meaningless to me. So the closest I get to understanding to this new system is look at every square millimeter of the Earth's surface, we have close to 1 billion internet addresses. Well, that seems to be a pretty appropriate infrastructure to facilitate the Internet of Things. So, we started. And I have to remind you, we're a collection of artists, architects, and engineers, and other people. So I think it's good to have a multidisciplinary team, because in the early stages of projects, we often think to ourselves, well, why is this necessary? What is this good for? And usually, it doesn't seem to be good for anything. But then the artist says, like, well, this could be an interesting conceptual piece. We could show this in a gallery, probably. Like, okay, that's good. So let's roll with it. And then all of a sudden, it ends up being good for something else. So, and this is one of those projects. We call this our Ground Zero project. But it's a digital window. And everybody has a digital window in their pocket, because when you take out your phone and you put on the camera, there's a kind of collapse that takes place in your phone with a camera on one side that films something, right, or sees something, and then a screen in your phone that shows exactly what the camera sees. Now, very simple object, but it does create a kind of mediated transparency, right? You can look right through your phone. It's a solid object, but you can look right through it because of the collapse of two little machines, the screen and the camera. So we said, let's put this in a window. So we said, like, okay, here it is. This is what we call the digital window. And right now, the window is now empowered by the net. It's connected to the internet. You can look outside. There's a digital mediation. You can also receive other things on it, right? So you can get the actual internet itself, or the local news, or anything else. Or when it's in the wall, you kind of automatically get your ultimate reality TV. We said, like, well, the people are going to think that this is kind of stupid. He said, no. This is our Ground Zero project. This is where it all begins. This is where the basic object that has significance in architecture, like the window, gets a digital mediation that occurs to it. So we went on. This is the dual state room. The dual state room is a kind of deep wallpaper. It's used out of old technology. These used to be signs, flip dot signs. They're very reflective on one side, and then they have a wood veneer on the other side. So in this particular room, you can have two spatial conditions. And these spatial conditions are very much like follow a kind of interior decorator rhetoric, you know, the kind of Martha Stewart rhetoric, right? Like the room could feel warm because it's woodsy, or the room can feel cool because it's a highly reflective paint. So what this project told us was basically that we could start to view the world in different scales, right? You can sort of see that your one skin is your first enclosure. You inhabit your own skin. Your second enclosure becomes your clothing. And then the third enclosure is the building around you. And what starts to happen if these three scalar conditions can start to communicate with one another, because all these conditions become computational. So that means when I'm hot, the room could actually start to facilitate a type of placebo effect and make me cool, so I don't have to take off my jacket or put my deodorant to the test. So, but then we got a little more serious. Then we started to say, like, okay, what happens to the envelope of the building? How do we start to deal with that? So we started to do a series of projects that deal with the envelope of the building. So this is the traditional building, and it has a furnace in the basement and a heat recovery ventilator, and it's a big machine. And with a lot of ductwork, it sort of covers the entire house, or even an office building. You have certain floors that are dedicated to the machinery, and then you need enormous amount of ducts to take care of the rest of the building. Now, these ducts take about 30% of your plan, or 30% of your section. That's a lot of space. So we said, what happens if we start to distribute that technology and actually make the entire of the envelope of the building a heating and cooling and ventilation device? So we turned to computers themselves, right? We took this project actually quite literally. Mark Weiser said the computer is going to embed itself in the environment. We said, okay, let's take these computers and let's take their parts and embed them in the environment. So here are CPU coolers. They're used to cool chips, and they're the smallest around, right? And when you put two CPU coolers back to back, you get a heat recovery ventilator. You can do hot, stale air, pump that out, make it run through here. That then heats this side, and you can get fresh air that comes in that is heated by the exterior air going out, right? So there are no heat recovery ventilators on this size in the building industry. They don't have it. They're huge, right? They're not as tiny as this, but we can find them in the computer industry, and we're actually realizing that this miniaturization of machinery can come in quite handy when you start to think about architectural facades. So then we have a series of these windows that we're continuously working on with different teams, including undergraduate students at Mechanical and Industrial Engineering. Some of their capstone projects are projects that we do together with them to hash some of these problems out. So in this case, this is maybe a little bit of an abstract image, but this is a section through a facade, and the glass sits here and here. And these things are made out of aluminum. And when it's very cold outside, you need a little thermal bridge here, because then your window doesn't get very cold inside, and there's all this accumulation of moisture and ice. So we replaced that thermal break with a thermoelectric device, or a Peltier device, which is a solid-state heat pump, can last over 100 years, has no mechanical parts, no rotating parts. And if you take that little device out there, your little thermal break, and you replace that by a solid-state heat pump, all of a sudden you have a window system that can heat and cool your building. And you don't need any ducts or anything else that obstructs your building. So this could be a very clean building with no machinery inside of it. Now, why are we not in business yet? That's because these things aren't very efficient. They're about 10% when you compare it to regular Carnot cycle of your traditional air conditioner, let's say. However, These things are subject to Moore's law, and they're getting more efficient every day, every year. So in the near future, this might be a viable solution. And when that future is there, we hope to be ready for it. Heating and cooling glass is the same story, but now it's embedded in the glazing itself. The previous projects were dealing with the window frames, and this was an attempt to embed it in glazing. So this slumped glass basically heats and cools your building. This was done with many. A lot of our projects we do with thesis students. Students at the University of Toronto play a huge role in the work that we do, because they do most of it. So this is the tunable sound cloud. It's by Manny. He was interested in chamber music. He played the cello. He wanted to create an architecture that would facilitate in real time different acoustical properties of a room. This room has acoustical properties. Half of it is wood. The other half is an absorbent material, so that I don't echo like crazy. This is a similar system. However, this object moves in real time and adjusts the acoustical properties of a room. So when you're dealing with music that is not electronically enhanced, like chamber music, the conductor can not only conduct the musicians, but also conduct the shape of the room itself to sort of create how sound reverberates. And this is what it looks like from the bottom. This is the breeze-through wall by Arthur Tseng. This is a project that deals with the desires of modernism. The desires of modernism turned everything into glass to create a distinction between interior and outside, to sort of remove that distinction, to bring the outside in. Here we took that to the next level, perhaps a more literal level. So now you don't only have glazing in your room, but the wind literally blows through your space, right? So there's the icy cold Toronto wind comes in here, but however, the envelope of this room is a heat exchanger, so you're literally inhabiting a heat exchanger. So the icy wind, all of a sudden, once it passes through your wall, turns into a nice Caribbean breeze. And then when it leaves the room again, it turns back into the icy Toronto breeze. But meanwhile, all that energy perpetually sort of recycles, and every sort of molecule of air hands over its energy to the other one, going in and going out. This is the oxygen curtain, another student project by May Shapna. Algae is a very interesting product. Lots of architects are looking into it now. What's interesting about it is that it seems to be, it's a very good carbon dioxide sequestration plant. So it's very good at absorbing carbon dioxide, and it does it more so than any other green species on the planet. So, for example, this little bag of algae sequesters as much carbon dioxide as a small mature tree. So we call it oxygen curtain because we see it as a possible curtain in a domestic setting, and inviting a curtain like this will sort of bring in a small forest into your living room. This is erratic chamber. He's wearing a very small brain sensor on his head. And this sensor senses the brain waves, and it creates an aura around you. So when you think different thoughts, these tiles change colors. And when you are in a social setting, basically you create this colorful aura around you, and the way you negotiate your social conditions with other people, architecture plays a mediating role in that. And very quickly, the last project is the soft hardware, soft computation. It's called I Am Blanky. This blanket, we were asked to participate in this exhibition, and they said, "What's the future of?" It was called stitches. What's the future of embroidery? And we said, like, okay, let's do a blanket. And what happens when this blanket becomes computational? So the blanket basically has a shape in real space, and when you lift it up or you manipulate it, there's a digital mesh that does exact same thing, right? So every flower here is a tilt sensor, and as you move the blanket, it communicates its space, or it communicates its shape into a virtual space. And it does that by literally embedding computation in the blanket. So here's the tilt sensor, and the tilt sensor is soft. So every petal here, this is the positive charge comes in here, and this is all negative charge, so it constantly creates a kind of short circuit. So this kind of loops around and creates different orientations. And then here are multiplexing chips, and they're constantly querying, like, okay, where are you orienting? What is your orientation? And then it communicates that to the digital mesh. And then this is the final product. So now it's actually the blanket literally has become the computer. And I think I'm running out of time. So the last thoughts of this was in an exhibit for about 5 months, and as an academic you need to publish. So we sent it to everybody, blogs, left, right, nobody was interested in it. And then all of a sudden Gizmodo picked it up, and they covered it. And after they picked it up, it went haywire. So it went everywhere, including Wall Street Journal showed up, and they all wanted to know, and they all published it. But the press these days, they say anything. All right? This blanket can do anything. According to the press, it could be used as a 3D scanner. It could be used to monitor patients. It could be in hospitals, and it could do all these things. And we said, well, when computation comes to a blanket, we decided the first thing it needs to know is its own shape, right? It can't do all these other things. But now it has become a feedback loop. And the second blanket that we're working on, we're doing with the Department of Occupational Therapy with Alex Miolidis. And this blanket starts to look promising, and we hope that this blanket will be able to do some things. And it starts to look like we'll be able to sort of study people with sleep deprivation disorder, right? They have different breathing patterns. We can pick up some breathing patterns with this new blanket. So this is the direction that it's going in. Right, thank you.